Okay, hi guys. So in this lecture we'll be discussing about classical and non-classical carbocation. So we'll just look into what is known as classical and non-classical in just a matter of few seconds. So classical and non-classical carbocations. Okay. So let me explain this with the help of an example. So if we have something like this, and Br here, so it is an example of classical carbocation. But if the Br is also sharing the positive charge along with the two CS2 carbons, then it is non-classical and this is classical. Okay, so non-classical carbocations will undergo rearrangement. Non-classical carbocations will undergo rearrangements and non-classical are actually more stable also. Non-classical more stable than classical. Why? Because of these reasons, that it is having complete octet, and second point is due to resonance stability. Okay, so what happens is the Br actually donates electron to the carbon atom, so thereby forming a bond between Br and C, this carbon atom and the Br. So also taking a Br positive on itself. That could be one scenario, and another could be it can actually withdraw this bond from this carbon atom and actually give this positive, the carbon is positively charged. So there is a bond formation and breaking step due to the positively charged carbon or carbocation, so due to which the sharing of positive charge increases within the compound, and hence the stability will also increase. Okay, so let us take some of the examples wherein we find formation of non-classical carbocations. So if we have something like this, and CS2 plus, then actually this can share the positive charged carbon atom with itself and can form a compound like this. Similarly, we can have something like CS2Br, we have already discussed. It can go and attack on this carbon. Similarly, we can have where it can attack to this positively charged carbocation. Okay, so nucleophile having lone pair is engaged in non-classical carbocation formation. This we can write that nucleophiles having lone pair is engaged in non-classical carbocation formation. Okay, so let me take some examples for the same. So if we have something like this and Br2, which is brown in color, is added in presence of CCl4, then what will happen is we will have something like this, plus it's a racemium mixture, so we would also have something like this. Okay, so this is actually colorless. So this is also a test for unsaturation, that the alkene when reacted with the brown colored bromine in presence of CCl4, then the brown color changes itself into colorless. So this is racemic mixture. So we'll take a look into how the mechanism of the reaction takes place. So mechanism is something like this. We have this cyclohexane ring, the double bond here. We have attached two hydrogen atom here, and we have obviously bromine. So what will happen is the double bond will actually attack on bromine, and this will form as a rate determining step for this reaction. So what will happen is the double bond will break, and it will have bromine with a positive charge roaming inside all the three atoms. Okay, so with this, after this, what will happen is the Br minus will actually see this opportunity and can attack on this non-classical carbocation. So what will happen is Br can attack either from front direction or from back direction. Okay, so what will happen is if it attacks from front direction, this Br, so it can come on this, and the other Br will go down the plane, and if it attacks from behind, then actually this Br will come in front, and the attacking Br will go down the plane, thereby forcing this Br to go up the plane. So this is how a racemic mixture will be formed. And let us look closely at how the Br is attacking on this. Okay, so if it attacks from the front on this carbon or on this carbon, doesn't matter. So it will force this Br to go down the plane, and if it attacks this carbon from below the plane, and then this will force this Br to go up the plane. Okay, let us look into some more examples of classical non-classical carbocation formation, specifically when we actually add Br2 in presence of H2O. So what will happen, we will have something like this, and this is called halohydrine. Okay, so what will happen is obviously you can form the E enantiomers of this. So what will happen is the released Br minus will be surrounded by OH and as OH is a ionic solvent, it will trap the Br. Meanwhile, some other OH minus will actually go and attack on this carbocation or non-classical carbocation. Okay, and form this product, which is called halohydrine. Okay, so what are the characteristics of this reaction? We will see the characteristics of this reaction in this lecture, and from the next lecture we'll be practicing some more examples on it. Okay, so characteristics of reaction would be as follows. We have something like, it is a hollow electrophilic addition reaction. So it is an example of, it is a electrophilic addition reaction. Okay, second point is the formation of non-classical cation is the redetermining step. The formation of non-classical cation is the rate determining step. Third one is overall mechanism is an anti-addition. So overall mechanism is an anti-addition. In case of hydrogenation, it was a syn addition. Okay, and presence of K1O4, cold alkaline 1% K1O4 or Beer's reagent, it was also a syn addition. But in this case, it's a anti-addition, in which two BRs or one BR, one OH will be placed in opposite sides depending on how the OH attacks the already existing non-classical carbocation. So with this we come to an end of this lecture, and in the next lecture we will be seeing some more examples on non-classical carbocation as an intermediate, or the reaction of alkene with Br2 in presence of CCl4 or in presence of H2O. So till then, good luck and goodbye.